acoustic wave is modeled by this time domain wave equation. And I was explaining why we have here time independent. I mean, for the electromagnetic wave, we have time independent equation. I said because the electromagnetic wave are propagating very fast, much faster than the acoustic wave. So when we send the pulse, the laser pulse, so the electromagnetic wave will propagate inside the tissue very fast, and it will generate the acoustic wave. And the ratio between the speed of the electromagnetic wave and the acoustic wave is too large. And this is why we assume that actually we take the mean of the electromagnetic energy over the pulse time, which is large compared to which is very small compared to the time scale of the acoustic wave. So this is why we assume that the electromagnetic energy wave is time independent. I mean, the equation, the system that model the propagation of the electromagnetic wave is time independent. And also, you are wondering why we are talking about wave electromagnetic wave, while we have here a diffusive equation. And again, this is because we are in the diffusive regime, and the diffusive regime, you can approximate actually the wave equation with this diffusion equation. So again, mu a is strictly positive coefficient in the whole space, and dA is a strictly positive function. So we assume that dA and mu a are unknown in some bounded domain, and they're known outside. And of course, here, since we send the wave from outside, so we assume that omega, the domain where we want to recover the two coefficient, is I mean the mouse. The domain occupied by the biological tissue of the mouse. And we assume that dA and mu a are known outside this bounded domain. For the acoustic wave, here, I mean, what the people consider in general is the space Rn is because they want to simplify the model. But normally, the true domain, the true problem should be defined in a bounded domain, because there is a big difference between the speed of the acoustic wave in the mouse and the speed of the acoustic wave outside of the mouse. So the acoustic wave cannot propagate outside, while the electromagnetic wave can propagate. Okay. Anyway, so the coupling is through this absorption energy, electromagnetic energy, and you see that U is the electromagnetic wave. It is strictly positive function, so multiplied by the absorption coefficient gives you the amount of energy, electromagnetic energy, that the mouse can absorb. Okay, and so we assume that the acoustic wave at t equals to 0 is 0. Anyway, so we measure the acoustic wave on the boundary. Again, the boundary is the mouse, and what we want to recover here are all the coefficients. This is an inverse problem. So we measure the acoustic wave for an interval of time between 0 and capital T, and we want to recover dA, mu a, and C of x. C of x is the speed of the acoustic wave. Okay. So if you have any question, please feel free to stop me anytime.
Okay, Faouzi, thank you.
Okay. So this is the inverse problem. So we measure the acoustic wave on the boundary, and we want to recover the three coefficient. But for medical doctors, the main, I mean, the important coefficient are dA and mu a, what we call the scattering coefficient, dA, and mu a, the absorption coefficient. The speed is not important here, but in order to well solve the inverse problem, we need also to recover the speed. I will explain you why. So since we have two steps here in this model, so in the inversion also we have two steps. The first step is you start with the data, so you invert the acoustic wave. Is acoustic inversion. So here you assume that we know the pressure feed on the boundary, and we want to recover at the same time the initial pressure mu A times U, and we assume that mu A, we assume that U actually is compactly supported here. Just to simplify the model, we assume that U is compactly supported in omega. And this is what the people, assume in general. So we want to recover at the same time the speed of the acoustic wave and the initial data. Okay. Now we assume that we recover the speed and the acoustic and the initial pressure, and we move to the second inversion, which is to recover the two optical coefficient dA and mu A from now the internal measurement mu A times U. And you see here there is a big difference. So here you have an internal function. So we want to recover dA and mu A from the knowledge of mu A times U, but mu A times U inside omega, okay, in the whole domain omega. Of course, here you know the source. You know the source. This is a new kind of inverse problem. And so with the first inversion is a little bit classical because it's like initial data to boundary problem. But the recovering the speed at the same time is a new type of inverse problem. For the optical inversion, is completely new. So you know internal measurement. You know this mu A times U inside the domain omega. You know the source, and you want to recover the both coefficients. Okay, so this is the big picture of the two inversion of the acoustic and the optical inversion. And let me give you a few observations related to these two inversion. So the people in general, this is the people who came with this idea of coupling acoustic and electromagnetic energy are physicists, and what they do in general, they assume that the speed is constant in the biological tissue. And also, they will stop at the first inversion. They will stop at the first acoustic inversion. They will not perform the second inversion. And the third observation is that the resolution is very limited in depth. And I will explain you why these three observations are important. And I will try to explain you through mathematical formulation, mathematical hints, why these three observations. Okay. Some physical hints. So why the people, the physicists assume that the acoustic speed is constant. This is because the biological tissue are approximately formed by water. 80% of the biological tissue is water. So this is why they assume that the speed is water, the speed of the water. And why they stop at the first inversion, they will never perform the second inversion. Yeah. This is because they have a very contrasted image at depth beyond the depth that we can achieve using only electromagnetic wave. And you see here here is a real data, and you can see the blood vessels of few millimeter of size very clearly, and this image is obtained through the system is very easy to realize. You just send the laser, you measure the acoustic wave. This is something that doesn't cost a lot of money, like MRI, for example. So it is very cheap image and with very good quality. And this is what the people get excited about this imaging modality, and a lot of research on this topic now. So they stop at the first inversion because this is what they get from the first inversion. They get a very nice image. I will explain why we have why we have so good contrast between blood vessels, and here we have a small tumor. And the third observation why the depth resolution is bad here in these imaging modalities, because the photo acoustic signal is very weak. I will also explain this later. So let us first start with the first inversion, the acoustic inversion, and here we will assume that the speed is known. Okay, so the speed is known, and we will assume also that the acoustic initial state at t equals to 0 is compactly supported. Okay, so what we do here, I'll just go back. Sorry about that. Just briefly, I'll just show you the first inversion. So here you have the first inversion. We have the acoustic wave, and again, what I'm trying to explain is just to assume that mu a times u just multiply by the characteristic function of the domain omega here at t equals to 0. So what we want to reconstruct, we want to reconstruct the speed and the initial state. And since the speed is the speed of the water, we'll assume that the speed is known. Okay. So the people who assume that the speed is constant is the speed of the acoustic speed of the water. Okay. So this becomes a classical inverse problem. And the most efficient way to recover the initial state, and this is what the people are using for a long time, is the reversal time method. So what is the reversal time method? And here I will introduce an improved version of the reversal time method. So you consider, so you what you do, you register the acoustic wave for an interval of time on the boundary between 0 and capital T, and you define a linear operator lambda that assigns the initial pressure at T equals to 0, the boundary measurement of the acoustic field on the between 0 and capital T. Okay, and what you do is just reverse the wave. You just substitute T by capital T minus T. And you have this function V. This function V is exactly the pressure P at X and capital T minus T. And at T equals to 0, we assume that, and this is the improvement here in this for the classical, compared to the classical reversal time method. We assume at capital T the wave is not 0. So the classical reversal time method, we assume that the wave is 0 at capital T, and also the initial speed is 0. But here we will assume that at capital T, the wave is not 0. Actually, the wave is exactly the solution of this harmonic problem with boundary data is exactly the pressure that we have at capital T. And why it is improvement because in general, at least in dimension 3, you can assume, since the wave is propagating at finite speed, so we assume that the wave will exit the domain at capital T. The capital T, the wave is 0. Since the initial state is compactly supported, so we assume that the wave will exit the domain, and this is in general is not true. So and this is why we assume we correct here the singularity. Actually, if we don't correct we don't add this initial state phi capital T, we will have a small jump at capital T when we reverse the wave, and this is why we add this boundary data. So if the pressure is 0, then you get 0 inside the domain omega. Now we assign to, so the reversal time operator, we assign the pressure on the boundary, the measured pressure on the boundary, the initial, the solution of V of X at capital 0, at 0, sorry, which will give you actually the exact initial state. If the reversal time works very well, it will give you exactly the initial state of the pressure P. Okay, so if you assume that the domain is not trapping, and if T is large enough, you can show that, and you find this method in this paper of Ullman and Stefanov, and there are many other papers dealing with the reversal time method. And if you multiply A, this operator, reversal time operator, by lambda, you get identity minus K, with K is a contraction in the energy space. You take the energy space, you can prove that for T large enough, this becomes the norm of K is strictly less than 1, and you have a contraction. Yet you can solve actually this inverse problem using Newman series. Anyway, so this is what the people use in general to solve the acoustic wave, assuming that, of course, here the speed is known. Now, what the future direction for this problem is to correct a little bit the speed and assume that the speed is a small perturbation of a constant, not a constant, but small perturbation of the constant, and try to recover the small perturbation and the initial state at the same time. And until now, the problem is still open. We cannot say that we can recover uniquely the perturbation and the initial state at the same time. There are some partial results, but the problem is still open. Okay, now we move to the second observation. So the second observation is why the physicists don't perform the second inversion. So they will only use this reversal time atom, assuming that the speed is constant. So the characteristic will be lines and just reverse the wave and recover the initial state geometrically. And this is what they get. They get exactly mu A times U. This is the initial state of the acoustic wave. And why they have a good image and they will stop there. This is because actually, if you see the product between mu A and U, assuming that mu A is piecewise constant, and just go back to the image here. So this is what you can see here is that mu A times U. This is mu A times U. And the absorption of the blood vessels is much different than the absorption of the tumor, for example, and the rest of the biological tissue. And this is why, because you have a very good contrast in the coefficient mu A. The mu A of the blood vessel is very different from the absorption of other part of in the image. And if you assume that mu A, for example, is discontinuous, and you know that from the Di Giorgi result, it's a very old result, if you look to the diffusion equation, this is diffusion equation. This is elliptic equation. It's elliptic equation. S is compactly supported outside of omega. So here, assume that it's 0 on the right side. So Di Giorgi result says that it was a big improvement at the time in the regularity of elliptic equation. He proved that actually the function is not only L infinity, the U is not L infinity, it's also in a Holder space, and the Holder coefficient alpha depends on the contrast, depends on the jump of the coefficient dA and mu A, if you assume that dA and mu A are L infinity coefficient. So what I'm saying here is that if mu A is piecewise constant, due to the elliptic regularity, you will see 0 alpha, okay? So you have here, what you get here, you have a product between a piecewise constant function and a Holder continuous function U. So this means that the product of both function, the singularity of the product of the both function, are exactly the singularity of the coefficient mu A. And this is why you have a good image after the first inversion. And here I give you an example with synthetic data. So here assume that mu A and dA are piecewise constant. You see dA is 4 outside this disk, and 1 inside. Mu A is 2 inside at 0.01 outside. And I computed this is G, the boundary condition. I consider it for the elliptic equation. And this is U. This is the solution U. And you see that U is smooth, and you cannot see this disk, this singularity in the image of U. But if you multiply mu by U, you get this, and you see that you can really distinguish between, inside and outside the singularity. So this is what the physicist will stop at the first inversion. This is because they have a good contrast, and this is exactly what about in this medical imaging. So the diffusion equation will give you the contrast because the coefficients are well contrasted, and the acoustic wave will propagate the singularity toward the boundary. So this is why it works very well. Okay. So if you consider this idea, I mean, the fact that the singularity of the product is the singularity of the mu A of X, if you want to recover mu A, it's like recovering the singularity in an image. So this is like an image problem. You have an image, you want to segment the image, you want to recover the singularity in the image. So there are many people who try to use this idea and to recover the coefficient mu A without, solving the second inversion. And one of the ideas, for example, if you take, so here U is always positive. This is a physics property of U. U is the fluorescence of the laser, cyclic positive function. And if you take the logarithmic of the product, you can separate between U and mu A, and you have smooth. So log of mu A is a singular function, piecewise constant function, for example, and the log of U of X is a smooth function. So you have, like in image, you have smooth plus singular, and there are many techniques to separate the smooth part from the singular part. And also we have this paper of Marcherzer and his colleague using the technique in image treatment, like Ambrosio-Tortelli approximation or Munfarsha-like functional to determine the singularity of mu A. Okay, so the only problem here is that in for physicists, for the medical doctor, okay, the image is very nice. So you can go back to the image. The image is very nice, etc., and you can see blood vessels. And but the point is that you need really to recover the value of the absorption and the diffusion coefficient. So you need real value of mu A and dA in order to say that the biological tissue that we see here, the yellow part, is a tumor or not, because this is how the medical doctor will judge. They need really the real value of the coefficient, not only the shape they need really the real value. So here in this method, you will recover the singularity, but you will never recover the value of mu A. What you can see here is just the jump, but you see the value here and here are not the real value of the mu A. They are just the value of mu A times U. So you need really to solve the second inversion, and this is what I will talk about. The rest of this presentation, I will focus on the second inversion. We call it the quantitative photoacoustic tomography, and I will explain you the third observation, which is the resolution depth. So why the resolution is very bad in depth, and this is the system that exists now. You can find it in hospitals. It works very well. So the system is based on this device. This device is the echography device, This is the same echography device, and just they just made a hole inside this device in order to send the laser, and they send the laser and they measure at the same time the acoustic wave generated by the laser, and they will see the image on the screen. And you can, if you look closely to the what the maker of these machine said about the resolution. They said they have 1 centimeter of depth, I mean penetration depth resolution, which is very large. When you talk with the physicists, they will say, "Not, we don't have 1 centimeter. We have only few millimeters. We have like 4, 5, maybe 6 millimeters depth. Depends on what region of the body you want to image." But is still much larger than the depth resolution if you use only the electromagnetic wave, which is 1 millimeter. Okay. I mean, what I mean by depth resolution is you fix the resolution. You fix the resolution. I said that the resolution is, what is the resolution? The resolution is the minimum distance between 2 points that between two small objects that you can distinguish. Okay. And when we talk about the contrast, contrast is the difference between the value inside and outside the tumor, for example. So the rest of the talk will, is related to the imaging, to the quantitative photoacoustic inversion and to the resolution in depth of this imaging modality. So there are many work on dealing with quantitative photoacoustic imaging, and also related to the acoustic inversion. The acoustic inversion is more, more classical inverse problem. I have many work on that. Yeah. Oh. Okay. So we have many works on the acoustic inversion, and as I said, the main problem is now to recover the part of the speed and at the same time the initial state. And the recovering the part of the speed is just to improve is just to well propagate the singularity of the initial state, because we will not use the speed, the acoustic speed, to have further information about the biological tissue. The main parameter, physical parameter that we want to reconstruct are the absorption and the diffusion. Okay, so here we want to recover part of the speed, the correction of the speed, or the correction of the constant, just to improve the recovery of the initial state. There are many work on the optical inversion, but since the data are quite new, so we have internal data. So we all the work on these optical inversion are new, are very recent, back to 10 years maximum. And so what the people did at the beginning, very beginning, was to assume that the critical point has no, the data has no critical point. The critical point are the point where the data will vanish, not the solution U, but the gradient of U will vanish. So we'll see that these critical points are a very important issue in solving this kind of inverse problem. Now I move to the first work. So this work was done in collaboration with Quirin in Columbia University, and what we try to do here, just to we try to actually we try to follow the physical setting. The physical setting is to send the wave, the acoustic, the laser illumination from one side, and to measure from the same side. Okay, and that was the first work dealing with, dealing with realistic measurement, because most of the mathematical work will deal with measurement on the whole boundary and laser illumination on whole boundary. And so just assume that here we send the wave from one side, and we measure from one side, and we also assume that in order to evaluate the depth resolution for this imaging modality, we assume that all the coefficients are depends only on y. Y is the vertical variable. So we assume that the media is layered. So here dA is lower bounded by the constant d0, and mu a is lower bounded by the constant mu0. Gamma m is this part of the rectangle, is in 2D, and omega is the whole rectangle. We assume that, and also the speed, here we assume that the speed is not constant, but is known, and also dependent on the y variable. And this is the first, first equation, the electromagnetic equation, and this is the wave equation, the acoustic wave equation. And you see here we added these impedance boundary condition because when you measure the acoustic wave on gamma m, you will use this device, and this device will reflect also the wave. And here we have a bounded domain. Okay, so we actually that device will absorb, using the transducer, will absorb a little bit, of the amplitude of the wave. So we have an attenuation here. So we added some attenuation on the boundary. This is a very realistic model. Okay, very realistic model, and just to to evaluate the depth resolution in this kind of modality. So of course here we assume that we know the speed of the wave, and the objective is to recover dA and mu a from the measurement of the acoustic wave on the boundary. Okay. So we assume that we measure P, the acoustic wave on the boundary, on gamma m, for an interval of time, 0 capital T, with capital T is large enough. I will tell you. So capital T is large enough. Capital T is larger than 2 times theta times h, with theta is related to the speed. Theta is related to the speed of theta is actually the mean of the speed on the intervals on the interval 0 capital H. And this is the first global inversion. And if you assume that the time is large enough, we have this weighted stability estimate. And you see these are the measurement on the boundary on gamma m. So you control, if you have two coefficients, dA and mu a, and mu a tilde and dA tilde. So you can control the difference between the two coefficients, mu a and mu a tilde, dA and dA tilde, by the difference between the two measurements generated by the both pairs. And you can see that beta appears here, and you have here power 1/4, so it's Holder stability. So in inverse problem, this is a very nice stability. And we have a really, explicit constant. You see, this is explicit constant Cm. And what is very important here to read is that we have a weighted stability estimate. So you have here U underline m power 5 is exactly given by this function. And this function is 0 on the top. It will be 0 here on the top, and it will be it will be 1 here on the top and 0 here on the bottom. So it decays exponentially from 1 to 0. Okay. So this tells you that actually close to the boundary where you send the laser and you measure the acoustic wave, you have a good stability because UM is 1. You see y is between 0 and h. So if you take y equals to h, you get 1 here. Okay. So this means that you have a good stability estimate close to the boundary where you send the electromagnetic wave when you eliminate the domain, and it decays exponentially. So this weight will decay exponentially. It becomes exponentially small, far away from the boundary, and you see here, if you multiply by 0, if you multiply by 0, it's like you divide the right hand side by 0, and you lose, you lose information about mu A and dA far away from the boundary. This is what we mean by deep penetration depth. And this is why we have a very good resolution close to the boundary and a very bad resolution far from the boundary of the elimination. And this was the first result that, quantify this effect and why we have, we lose a resolution far away from the boundary. And actually I will not talk about the details of the proof. I will talk about the details of the proof of other result. But just keep in mind that the solution of the of this optical equation, this diffusion equation, is decaying exponentially in depth. Okay. And since here what you, from the internal measurement, what you recover is the solution u times mu a. And if u is very small, then of course you will lose information about the optical coefficient mu a. Okay. So this is the first result. Now I move to the second result, which will, generalize this stability estimate in the whole domain, but we will not quantify the penetration depth in this result. We'll just quantify how the solution will decay exponentially far away from the source. So in this model, we assume that the laser source is a Dirac function. Okay. So we assume that we are in R power n, and we consider this optical solution. So the measurement in the photoacoustic, in the quantitative photoacoustic are mu a times u. So here we consider two measurements, 1 and 2. You have two excitation and corresponding to two position of this Dirac function. So C1 and C2. C1 and C2 are different outside the domain omega. Of course, here we assume this regularity for the coefficient dA is lower bounded than the C11, mu A is lower bounded than the C01. And we want to recover dA and mu A from the measurement of these two functional inside of omega. So we want to recover dA and mu A from two functions, which is, the degree of freedom matches very well the data. So the data, you have two functions, and you want to recover two functions. So this work is in collaboration with Eric Bonetier and Morad Chouri. And we have this stability estimate. So what we showed first that, of course, here the solutions are strictly positive. This is like the green function. Since we have Dirac function, it's green function, they are strictly positive everywhere. And actually, we proved that if you take two solutions, if you divide U2 by U1, you take the gradient, we proved that there exists a small ball close to the X1 and X2, where the gradient of the ratio in L2 norm is larger than eta, with eta is strictly positive constant. And this tells you that the two solutions are not, the gradient of the two solutions are not linear. Are linear independent somehow. And now we consider two pairs of coefficient dA mu A and dA tilde mu A tilde. And we assume that we know these coefficients on the boundary gamma, on the whole boundary of omega. And we recover this stability estimate. This is a Holder stability estimate. And gamma will depend on the set d lambda kappa. And here I will explain a little bit the result, how we obtain the result. So we have a Holder stability estimate, but this gamma can be very small because this is like the result in the whole domain. Okay, that's in the whole domain, so the gamma can be very small. And if the gamma is small, then this usually when we have a Holder stability, we think about the well-posed inverse problem. But if gamma is, I don't know, 0.01, you can consider this problem that ill-posed inverse problem. So again, for the people who are not familiar with the inverse problem, we control the coefficient, the difference between the two coefficients by the difference between the data. And this gives you an idea about how, the algorithm will work. If you, for example, use an iterative algorithm to recover the coefficient from the data, this tells you that the convergence is holder. It's like n is the number of iterations, you get convergence 1 over n power gamma times the constant. Just briefly, the behavior of the solution itself. You see here from the data we get mu a times u, and you see if u is very small. Again, if u is very small, so u is 10 minus 3, you will never recover mu a of x anywhere. So this is why we quantified, how the function u, the green function, will decay exponentially far from the source. So the source is xc. Yeah, the source is xc. If you consider constant coefficient for this elliptic equation, the result is known. You just recover the result from the asymptotic expansion of the Bessel function. This is the green function in any dimension n. And what we did, actually, we proved this result. Actually, we searched this result in the literature. We couldn't find it, so we proved it. And then this is a very important result, but the physicists do not know about how the behavior of the solution in terms of the coefficient lambda and kappa. I saw many wrong result in presentation of physicists about how the decay of the green function depends on the lower bound of dA and mu a and the upper bound. And you can see here the solution will decay exponentially far away from the sources. If you are far away from the elimination point, the solution u is small, very small, and then of course you will lose the resolution and in depth, and you will never recover the coefficient mu a and dA. Anyway, so let me briefly explain you the result. I think I have how many minutes left? Is 5 minutes? Is it okay?
Yes, it's okay, Faouzi, okay.
So the whole idea here, again, we know. Let me just remind you the problem. So the idea is you have mu a times u. You have two solutions corresponding to Dirac function, and you want to recover dA and mu a. And again, these are internal measurements. You know, these functional everywhere in omega. So the idea, actually, the idea came from this first paper that treated the photoacoustic quantitative photoacoustic inverse problem. Is Bolon and Ullman in 2010. And the idea is, I don't think we have. This is the only. I think this is the only idea it works for the moment. You take two solutions, U2 and U1. Again, the two solutions are strictly positive function. You see it from here. You see it from here. They are positive, strictly positive function. And if you divide H2 is the measurement. H2 is U2 times mu A. H1 is U1 times mu A. If you divide H2 by H1, you get U2 over U1. And simple calculation will lead you to this system. So you can prove that V, U2 over U1, is a solution to this elliptic equation, where sigma is dA times U1 power 2, and V is exactly U2 over U1, but it is H2 over H1. And since you have the measurement H2 over H1, you know V. So here, you see, we move it. We have an elliptic equation, but let us see what we want to recover, what we have. We have V, and we want to recover sigma. This is the first step, okay? And, we moved from an elliptic equation. So the first equation is elliptic equation to a transport equation, a steady state transport equation. So you know V, you want to recover sigma. This is a steady state transport equation. And this is why I said that the singularity is well propagated because we have transport equation behind, and this is exactly the transport equation what we want to solve. So we know V in the domain omega, and we want to recover sigma. We know also V on the boundary. And so this is a steady state equation, and if gradient of V does not vanish, and this is where critical point will play an important role, is if gradient of V does not vanish, you know that you can recover sigma using characteristic method, any nice method that you
لا لا لا
use.
ما لكوش علاقة، مش واحد. أنا حبيت نقول لك حاجة الأساس إن هو الولد
and
الولد أخذه.
once you recover sigma, so in general, gradient of V can vanish. You have critical point, and there are many very fine results in analysis dealing with a critical point and how big they are, and what is the multiplicity of critical point, etc., etc. And what we know, for example, in dimension 2, we know that the critical points are isolated point and they have finite multiplicity, etc. And actually, we have some result. Alessandrini in 1986, he proved and then we just show you the path, how he solved this inverse problem. The main idea is you just integrate by part, you multiply by V, integrate by part. This is what you get. You get this equation, and this power is coming from the interpolation of L2 and H2. And you see here, V is something that you know. So you control V, V minus V tilde. V is generated by the pair mu A dA. V tilde is generated by mu A tilde dA tilde. Okay. And you know, again, you know sigma on the boundary. Sigma is this guy here. You know it on the boundary, just assume it equals to 0. So here, if you forget this term, you can control sigma minus sigma tilde times gradient of V power 2 by the difference in the data. Again, the only problem is that the gradient of V can vanish. And when gradient of V vanish, we lose information about sigma. Okay. So the first work, they assume just the gradient of V doesn't vanish. Okay. So how to deal with the critical point? As I said, Alessandrini, he just used the unique continuation of elliptic equation. So you say V is the solution of elliptic equation. This is elliptic equation. U1 is strictly positive. So gradient of V cannot vanish in a ball. If it vanishes in a ball, it vanishes everywhere. It's like a holomorphic function. You know, the function. So the critical point has fine multiplicity, and the multiplicity is given by C. C is related to this is R here, small ball. So anyway, you quantify how the gradient of V is lower bound in terms of R, with R is the radius of the ball, and use that to derive this stability estimate, and you just recover sigma. Once you recover sigma, so assume that you have dA times U1 power 2, but you want to recover dA, you want to recover mu A. So actually, you can easily prove that 1 over U1 is a solution to this second elliptic system, with sigma here is the sigma that you recovered in the first step. Okay. If you have sigma, then you recover W, and W is exactly 1 over U1. If you have 1 over U1, you have U1, you divide by U1, you get mu A, you divide by U1 power 2, you get dA. Okay. And we can recover this stability estimate. So again, this power here, gamma, this power gamma depends on the vanishing order C here of the gradient at the critical point. And this is why C can be very large, and then gamma can be very low. Of course, if we don't have any critical point, we will recover Holder stability estimate with gamma is very close to 1. Okay, so this is the guideline of the proof. I have one more recent result, but I think I don't have time to present it here, related to depth resolution, and this is a very new result with my postdoc key she. So here, just the stability estimate is local, and actually we proved that the stability estimate, the Holder power and the stability estimate will increase if if R tends to 0. It means we are closer to the boundary, the impact point of the laser. Okay, here we assume we prove that we have. Here we used many measurements. So the first point, we used many measurements, not only one measurement, and that is consistent with the physical problem. Because physical problem, they take many images in few seconds. Okay, and we made it local by actually modifying the second step in the inversion. Just here you see in the second step we solved the analytic equation in the whole domain, and that makes the inversion not local. If you want to maintain locality, you need to modify this step and to solve the problem locally. And this is what we did. We introduced a Cauchy problem satisfied by the coefficient dA. And for the Cauchy problem, we can solve the Cauchy problem. So we actually showed that dA satisfies this Schrodinger equation. Since we assume that we know the coefficient dA on the boundary, since sigma is the coefficient that we recovered from the steady state transport equation, so we know this coefficient, we know this equation, and we know the boundary, the data boundary, so we can solve the Cauchy problem in this area here, and we can quantify, and this is the first that quantify the stability in the Cauchy problem using a well-suited Karleman estimate. And this is a very new result. So we proved this stability estimate that shows that we have a very good resolution if you are closer to the boundary. And this result will generalize the result with QRN dealing with layered media. Okay, I think I reached these are some numerical reconstruction of the coefficient dA and mu A using this method. And it works very well, actually, pretty well. If you are close to the boundary, it works very well. And we understood finally why it didn't work. I mean, many people were struggling to recover the coefficient dA and mu A in the whole domain. This is because U and the solution U is very small because it is solution to the diffusion equation. It's very small inside the domain. So it's hopeless and you cannot recover the coefficient dA and mu A using such solution. So if we confine ourselves to the part of the boundary where we eliminate the domain, U is large enough to allow to recover dA and mu at the same time. Okay, so we move to the conclusion. Some few remarks. So we derived some pointwise Holder stability estimate of the quantitative photoacoustic imaging, and actually the stability is consistent with experimental observation that say that we have a very good resolution when in the region where close to the optical illumination, and the resolution will deteriorate exponentially far away. So what we will do next is we want to propose an algorithm that solves both inversion, acoustic and the optic inversion at the same time, the same as in the layered media. And also there is a very interesting issue is the frequency dependency on the attenuation and the attenuation of the photoacoustic imaging. Here we assume that the coefficients are frequency independent, which is not true in general. So frequency independent means in time domain means that the coefficients are time dependent. And this is a more challenging problem because if you change the measurement, then you change the data. And you cannot divide as we did the beginning from the two solutions in order to recover something that is related to the second system. Another way now there is a very interesting problem method to overcome the weakness of the photoacoustic signal is to send two photons. is a two-photon absorption. Many people excited about this. And the principle of two-photon absorption model is to send a stronger signal in the domain omega. But here we have to be careful. The magnitude of U will not improve. It's just the fact that using two photon will improve the imaging functional. Actually, the model becomes nonlinear in terms of U. You have quadratic term, and we have actually we have few results related to this model because of the nonlinearity of the equation. There is another method to improve the photoacoustic imaging to send nanoparticle, metallic nanoparticle inside the domain, and using a very weak electromagnetic wave, you can amplify the photoacoustic signal using the plasmonic resonance, and we already did some work in this direction with Margot Vautrin in 2018. You can find all these references. I mean, the reference cited related to my work on my webpage. So thank you very much for your attention, and I will be very happy to answer your question.
Thank you, Faouzi. Is there some questions? No questions? Yes? Fahmi. Go on, Fahmi, yes.
Yes, thank you. Thank you, Faouzi. I enjoyed the talk, really. I have two questions. First one related to the stability. So it's a nice stability result, older type.
Which one?
The second one, let's say
this one.
Anyone, no problem. So my question is general. So it's quite strong stability, but are you satisfied with this result, or you want to prove something optimal, or can we improve it, or no need?
So I mean, the main problem, I mean, in this stability is the gamma is non-local.
Yes,
Gamma is non-local, is the whole domain.
Yes.
And because again, is because we have this global inversion here. So once we recovered the sigma from the steady strong transport equation, in order to recover U1, we need to solve the whole. I mean, we need to solve this elliptic equation, the whole domain. This means that we need to use the data on the whole domain. Since the data in the data in the domain, in part of the domain, the data is useless because the solution is too small. So if the solution is too small, I said the measurements are not good. And this is why we, in the second version, I mean, the second stability estimate, we wanted to avoid using this non-local equation by trying to solve this Cauchy problem. So the Cauchy problem, so again, we recover sigma, we have sigma, so we have the Laplacian of square root of sigma over square root of sigma. And we, assuming that we know the coefficient on the boundary, so we can make it almost local, because we can start, I mean, propagating the information from the boundary. We know the Cauchy data of square root of dA, and we propagate the information inside, using of course the knowledge of the coefficient. You see, the knowledge of the coefficient locally. We don't need to recover the coefficient sigma everywhere. Okay. So again, I mean, the first inversion is local because it's a transport equation. So we can solve it point by point. If you know sigma on the boundary, we just follow the characteristic and solve recover sigma at each point where you want to recover. So the first step is local. You can really solve locally close to the impact point, but the second inversion is not local. And this gamma actually is like the worst case. In worst case, the worst rated to the highest multiplicity of of the critical point of this gradient inside the domain omega. So what I expect, here in this stability estimate gamma is very low. And actually, this can we checked this in our numerical results. Actually, in our numerical result, many other works, they found out that the recovery is not so good because
we cannot improve it in this configuration, let's say.
Yeah.
And what happens? And also, do you know numerical works? What happens if we take more data, more sources? Does it improve or?
Yeah, of course it will improve. It will improve a lot. So there is a requirement. The condition on the sources here, I didn't say. You see here, in order to make it local, and you can solve it with one data. This is transport equation. You can solve it with one data. So if you assume the gradient of V does not vanish, for example, you assume it in any point, you can recover it in any point. So if you add data, you can solve this equation using this system. This is a linear system. You can write in terms of gradient of logarithmic of sigma. It's like the matrix M times the gradient of logarithmic of sigma equals to N. So you know N, you know M, just invert the matrix. Okay. So the more data, the better is.
Okay, thank you.
Thank you.
Is there other questions? Okay, Faouzi, thank you very much.
Thank you, Nabil. Thank you.
And I hope see you again in our center, or
I hope to see you all again.
You have to invite him to Dammam.
Very soon in Tunisia.
You are welcome in Dammam, yes.
Oh, thank you.
You have to invite him.
Thank you.
Thank you very much, Faouzi.
Thank you. Take care. Bye-bye.
Bye-bye.
Merci, Faouzi. À jeudi.
Comment?
À jeudi.
À jeudi, oui.
Jeudi, comme d'hab. Ça marche.
Oui, ça marche. À bientôt. Salut.
Allez, bye-bye.